Today we start this unit on functions. We're going to be talking about lots of different things having to do with functions. Particularly today, we're going to talk about even and odd functions, and then we're also going to talk about arithmetic combinations of functions. So an even function is a function where f of negative x is equal to f of x. What that means is whatever y value you get when you plug in the opposite of x is the same as the y value you get when you plug in x. So another way to see this is if x comma y is on a graph, then negative x comma y will also be on the graph. Now in terms of symmetry, what that means is that our graph will be symmetric with respect to the y-axis. Right, so if you imagine x comma y on one side and then negative x comma y on the other side, we can see that there is a symmetry. It's that point just reflected across the y-axis. A great example of an even function is the function f of x equals x squared, just your basic quadratic. So if you were to plug in positive 2, square it, you get 4. If you plug in negative 2 and you square that, you also get 4. So no matter if you plug in x or negative x, you still get the same y value. Now algebraically, a quick way to check whether or not something is an even function without needing to graph it is to plug in negative x into the function and then see what the result is. If the result is exactly the same, which it is in this case, then you know it is an even function. Now for odd functions, we would say a function f of x is odd if f of negative x is equal to negative f of x. So in other words, if you plug in the opposite of x, your result is not going to be y, but the opposite of y. Another way to put this is if you have a point x comma y on the graph, then negative x, negative y will also be on the graph. Now what this means in terms of symmetry, if you have xy on the graph and you also have negative x, negative y on the graph, this means that the function has symmetry with respect to the origin. A great example of this is f of x equals x cubed. So, for example, we can plug in 2 again. So 2 to the third is equal to 8. But if you plug in negative 2 to the third gives you negative 8. So 2 comma 8 is a point. Negative 2, negative 8 is also a point. Algebraically, we'll do the same thing as for an even function. You plug in the opposite of x, and if after you've plugged it in and you've simplified it, if your result is the exact opposite of plugging in x, so in this case, negative x cubed, then you know it is an odd function. Okay, so for an even function, you plug in negative x, you get the same thing. For an odd function, you plug in negative x, you get the exact opposite. Now you're not always going to have one or the other. You might have something that's completely different, which simply means it's neither an even function or an odd function. Not all functions are going to be one or the other. Now just as a note, we saw that an even function was symmetric with respect to the y-axis. An odd function is symmetric with respect to the origin. Is it possible for us to have symmetry with respect to the x-axis? What does symmetry with respect to the x-axis look like? It means that for some value, you have one value above the x-axis and one value below the x-axis. You would have 2 points, but they would have the same x value. Now what's wrong with that? What's wrong with that is that if you had that to be the case, then whatever you're working with would not be a function. So if that helps you kind of remember the symmetry aspect here, an even function, symmetry with respect to the y-axis, odd function, symmetry with respect to the origin. Neither of them can have symmetry with respect to the x-axis, otherwise it won't be a function. All right, let's take a look at example 1. Is f of x equals the absolute value of x even, odd, or neither? So without having to graph it, we can algebraically determine this by plugging in the opposite of x and simplifying this as much as we can. Now, since it is the absolute value here, the absolute value of negative x is going to be the same as the absolute value of x. Since this is exactly the same as plugging in positive x, we know that this is going to be an even function. Now, if you were to graph this function and you wanted to see the symmetry, the graph f of x equals the absolute value of x turns out to be this V shape, and you would see that there is symmetry with respect to the y-axis, which is what we expect for an even function. Take a look at example 2. Is g of x equals x cubed minus x even, odd, or neither? All right, we'll do the same thing. Plug in negative x. We have negative x cubed minus negative x. So that's negative x cubed plus x. Another way to write this is if you were to take out the negative, you would have negative parentheses x cubed minus x. And writing it this way can help. You don't have to write it this way, but it can help for some of you who might find it more visually appealing to see that this is in fact the exact opposite of our function g of x. So in this case, because it is the exact opposite, we know this is going to be an odd function. Example 3. Is h of x equals x squared plus 1 even, odd, or neither? Do the same thing. Plug in negative x into our function. So we have negative x in parentheses squared plus 1. We know that squaring a negative number will just end up being positive x squared. And as you can see, this is the same as plugging in x into our function. So since it's the same, we know this is going to be an even function. Now for this, you can imagine, or you can actually graph if you'd like, the graph x squared plus 1. And this is just a parabola, but it's shifted up 1. And it still will have symmetry with respect to the y-axis because shifting it up 1 won't affect the symmetry across the y-axis. Example 4. Is f of x equals x cubed minus 1 even, odd, or neither? Plug in negative x. Negative x cubed. Well, if you cube a negative number, it will stay negative, so this will be negative x cubed minus 1. If it helps, you can try factoring out a negative, and this is negative x cubed plus 1. So it's the opposite of x cubed plus 1, which is not the original function. The original function was x cubed minus 1. So this is neither even nor odd, so we would just say this is neither. All right, let's talk about arithmetic combinations of functions. So we have different functions, and we can combine them by adding, subtracting, multiplying, and dividing. The one thing to note is that addition and multiplication are commutative. What does that mean? So when we say that they are commutative, that means that the order in which we add or multiply the functions does not matter. However, subtraction and division are not commutative. So the order here does matter. Which function comes first, which function comes second. Let's take a look at example 5. If f of x equals 2x minus 3 and g of x equals x squared minus 1, find the following. Now for this notation, just so you are aware, this f plus g and then parentheses x parentheses, this does not mean you are multiplying by x. This just means that both f and g are functions in terms of x. This is, you can think of it as a shorter way of writing it. Instead of writing f of x plus g of x, you only have to write the of x once. So same goes with the f minus g of x, f times g of x, and f over g of x. Okay, so for the first one, here we are adding. So adding is 2x minus 3 plus x squared minus 1. And then combine anything that can be combined. It looks like the minus 3 and the minus 1 can be combined. and that leaves us with x squared plus 2x minus 4. Next we have subtraction. So in this case, just make sure that you are subtracting everything in the second function. So 2x minus 3 is f of x, and then we want to subtract all of g of x. So this is going to be minus x squared plus 1. And then we can combine like terms, so we have negative x squared plus 2x minus 2. In the next example, f times g of x, we are multiplying. Just be sure that you put both functions in parentheses to be sure that we end up distributing everything appropriately. So this ends up being 2x cubed minus 3x squared minus 2x plus 3. Alright, nothing to combine there, so that's our answer. Last one, we have f over g of x. So dividing 2x minus 3 over x squared minus 1. And there's nothing here that we can simplify. You could factor the denominator to x plus 1 and x minus 1, but it's not going to help us cancel anything out, so we can just leave our answer as so. Alright, so as we talk about arithmetic combinations of functions, we also want to talk about the domain when it comes to combining functions. So the domain of an arithmetic combination is all real numbers that are common to the domains of all functions. The one combination that we do have one additional restriction is if you are dividing two functions. So in the case of f of x divided by g of x, there is the one further restriction where g of x cannot equal 0. So previously, g of x could equal 0 when it wasn't in the denominator. But once you divide the two functions, you want to make sure that you include that as part of the domain restriction. So in other words, if you are trying to find the domain of the new function resulting from a combination of functions, it's going to be all real numbers that are in the domain of the resulting function as well as the original functions. So in other words, all domain restrictions from the original functions will carry through. Let's take a look at some examples about domain. So given f of x is equal to the square root of x minus 2 and g of x is equal to x plus 1, determine the domain of f of x plus g of x. Okay, so before we get into the domain, let's just write out what that combined function is. So that would be the square root of x minus 2 plus x plus 1. Now, were there any restrictions before we combined? Well, that square root we have to take care of, so x minus 2 has to be greater than or equal to 0. Solving that, we have x has to be greater than or equal to 2. And then look at g of x, there were no restrictions on that, there were no square roots, no denominators there. And then adding the two together, we have that combination, we just still have that same square root and nothing else new. So we would write x is greater than or equal to 2 for our domain, or in interval notation, that would be square bracket 2, comma, infinity, parentheses. Let's do an example where we do have division. So f of x divided by g of x. So let's write out the combined function, square root of x minus 2 over x plus 1. So start off with the original restrictions from the original function. So x minus 2 has to be greater than or equal to 0. We knew that already. Now the second additional restriction that has now resulted from dividing the two functions is the g of x in the denominator cannot equal 0. So x plus 1 cannot equal 0, which means x cannot equal negative 1. Now when we express this as in interval notation, well, x being greater than or equal to 2 actually already means that x cannot equal negative 1, right? Because negative 1 is not greater than or equal to 2. So in this particular case, we can actually get away with still just saying square bracket 2, comma, infinity for interval notation. It is still important to check. For example, if in the denominator you had x minus 3, then you would know that x could not equal positive 3, and then you would have to change your domain to go from 2 up to 3, not including 3, and then from 3 up to infinity.